In this section we will discuss several operations that will combine given sets to yield a new sets. Some operations in sets are union, intersection, difference, symmetric difference and complements. Given two sets A and B, the union of A and B is defined as the set A, union B, is equal to a set of X, such that X is an element of set A, or X is an element of set B, or means X belongs to either in set A, or in set B, or in both sets. Union of sets can be illustrated by this Venn diagram. This is another operation of sets. Given two sets A and B, the intersection of A and B is defined as the set A intersection B is equal to the set of X, such that X belongs to set A, and X belongs to set B. The Venn diagram of intersection is shown. Two sets, A and B are disjoint if A intersect B equals to empty set. Another operation of set is difference. The difference of two sets A and B is equal to X, such that X is an element of set A, and X is not an element in set B. The difference is also called the relative complement of B and A. Elements of the new sets consist of all elements in A that are not in B as shown in the Venn diagram. If A and B are two sets, we define their symmetric difference as the set of all elements that belong to set A, or to set B, but not to both X and Y. We denote it by delta. Another operation of set is complement. The complement of a set, A, contained in a universal set U, is the set A, complement equal universal set minus set, A. A complement is illustrated by Venn diagram. Another operation of set is disjoint set. Two sets, X and Y, is pairwise disjoint if X intersect Y equals to empty set. For example, the set 1, 7, 9 and set 2, 6 are disjoint. The collection of sets, S is equals to sets of 1, 4, 5 and 2, 6 is pairwise disjoint. In a Venn diagram, given two sets, A equals to 1, 2, 4, 5, 7 and B equals to 3, 5, 6, 7, identify A, union B. A, intersect B. A, difference B. B, difference A. The answers are illustrated on the screen. Next we will look into the properties of set operations. The operations on sets that we have defined satisfy algebraic properties. Let U be a universal set, and A, B and C subsets of U. The following properties hold. Associativity properties. Commutativity properties. Distributive properties. Universal set properties. Complement properties. De Morgan's laws for sets. Idempotent properties. Bound properties. Absorption properties. We try to prove De Morgan's laws for sets. A common style of proof for statements about sets is to choose an element in one of the sets and see what we know about it. Suppose that X is an element of complement of A union B. Then we know X is not in set A, and not in set B. The proof of the first De Morgan's law is shown in the video without using the Venn diagram.
Hi, in this video we are going to discuss about the written proof of De Morgan's law, and this is the part 1. We have already learned how to prove these laws or identities using Venn diagrams, and now we are going to discuss about the written proof of these identities, right? So the first identity or law says the complement of A union B is equal to A complement intersection B complement, right? So this is the first law, and if we take the left hand side and assume that X is an element of A union B complement. So from here we can say that X will not be an element of A union B, right? Since it is an element of the complement set of A union B, it will not be an element of A union B. And since it is not an element of A union B, that means it is not an element of A, and it is not an element of B, right? Since it is not there in their union, it will not be in any of the sets, right? So X is not in A and X is not in B. That means X is definitely there in A complement. If X is not in A, it has to be there in A complement, and X has to be there in B complement also, right? So if it is there in A complement and B complement, it will definitely be there in their intersection. That means X will be an element of A complement intersection B complement, right? So here we have got X is an element of A union B complement, and here we have arrived to a situation where we could prove that X is an element of A complement and B complement. That means A union B complement is equal to A complement intersection B complement, right? And now let's prove the second part, or the second law on the right hand side. The second law says A intersection B whole complement is equal to A complement union B complement, right? Again we'll assume X as one of the elements of A intersection B complement. If X is the element of A intersection B complement, that means X is definitely not an element of A intersection B. If X is not the element of A intersection B, there are the possibilities that X is not an element of A, or X is not an element of B, right? That means X is an element of A dash, or it is an element of B dash, right? If X is not an element of A or X is not an element of B, that means it is either in A complement or it is there in B complement, right? That means X is definitely there in A complement union B complement. If it is in any of these A complement or B complement, it will definitely be there in the union of A complement and B complement, right? That means from here we could prove that A intersection B whole complement is actually equal to A complement union B complement, right? So this is the written proof of these two laws, or the first two De Morgan's law, right? And after this we have the second part of the written explanation of rest of the De Morgan's law. So keep watching Math Smart, and bye bye till then.
Cardinality of a set A. In symbols, A is the number of elements in A. These are some examples of cardinality. infinite cardinality. Countable, for example, natural numbers or integers; uncountable, for example, real numbers. Now we are going to explain what is the multiplication of sets. Given two sets, S and T, where S is an element of S, and T is an element of T, then we can form an ordered pair, S, T, with S as the first element, and T as the second. For all S, T, with, the set is represented by, if T equals to S, then the multiplication set S, times T, equals to S times S, which is S squared. The ordered pair has the property that, two ordered pairs are equal if and only if, their first elements are equal and their second elements are equal. Given two sets, A, B, and B, A. For n set. To determine the numbers of ordered pair, if given two sets, X and Y. Example on ordered pairs. The answer is